other types of techniques, in this case, evolutionary programming techniques, with the latest foundation models, which are getting increasingly powerful. And I actually want to see in our exploratory work a lot more of these kind of combinatorial systems and sort of pairing different approaches together. One of the things, the self-improvement, someone discovering a kind of self-improvement loop would be one way where things might accelerate further than they're even going today. And we see that before with our own work, with things like AlphaZero, learning chess and Go, starting from random with self-improving processes. So we know it's possible, but again, those are in quite limited game domains, which are very well described. So the real world is far messier and far more complex. So it remains to be seen if that type of approach can work in a more general way.
So it's been about 2 weeks since Google DeepMind dropped AlphaEvolve. AlphaEvolve had an evolutionary process that, among other things, improved itself. It's a step towards self-improving AI. And now, just about 2 weeks later, this is Sakana AI. We've heard from them before. They introduce this, the Darwin Godel machine, open-ended evolution of self-improving agents. So both AlphaEvolve and this Darwin Godel machine kind of approach it from a similar angle. You can think of it as kind of a parents and offspring, parents and children. If a new process is created that seems like it's better, it's able to accomplish a task better, more efficiently, that becomes sort of a new branch on the tree. And we try to go down that path to discover if there's even sort of a better approaches down the line of that child. If it's offspring, if you will could potentially be even better in some way. This chart, I think, illustrates it really well. So this is a benchmark for coding. So we're testing it on a coding benchmark. We'll talk about it in just a second. But as you can see here, 0, that's kind of the beginning. So now we have 1, 2, 3, 4, right? So kind of going across. And each one is measured on how many tasks they can do. So the red ones performed poorly. They did 10 tasks and no basic functionality, so they're kind of useless. Yellows are okay-ish, right? They did 60 tasks, so a little bit better. And green did 200 tasks. It doesn't matter. We'll get to the tasks later. The point is green does well, red does poorly, and yellow's kind of somewhere in between. So in this evolutionary search, the red ones are kind of killed off, right? They go extinct. Their sort of offspring don't continue. They don't propagate. However, the green ones do, right? So if we come up with a new agent, a new process that does well and can accomplish a lot of tasks, it gets to have kids, so to speak. It wins the evolutionary game. So in this case, you can see this line of all champions, all greens eventually becomes the best agent here, the star agent. So both the Darwin Godel machine and AlphaEvolve use this evolutionary approach. AlphaEvolve, it's kind of in the name. So that's the Darwin part, right? So that's the evolution part. What is Godel? So Kurt Godel was a mathematician. He was influenced by Alan Turing and in turn influenced Jürgen Schmidhuber. So this is from the Sakana AI blog post. They were the ones behind this paper. So they're saying that this Godel machine was proposed originally by Jürgen Schmidhuber. And this was a hypothetical self-improving AI. It would solve problems by recursively rewriting its own code, and it can mathematically prove a better strategy, making it a key concept in meta learning, or learning how to learn. They point out that this isn't quite what Jürgen Schmidhuber had in mind. This isn't the same thing that he proposed, because he had this assumption that this machine would be able to mathematically prove that it's going to be better before adopting the change. Here they're doing something similar. They're using these open-ended algorithms like Darwinian evolution to search for improvements that empirically improve performance. Or as the kids say nowadays, FAFO, right? So you kind of test a bunch of different things and you see what works and what doesn't. And you test it with some criteria so you can empirically know if it's working or not. You see the results. So here in their paper, they know that a lot of research today, it's constrained by human-designed fixed architectures. They can't autonomously and continuously improve themselves, right? A lot of it is limited to smart people doing hard work, how much time it takes, etc. With AlphaEvolve, we're seeing more and more of this kind of relying on AI, on machine learning, on these sort of systems to try to improve certain processes. They were able to improve hardware as well as Gemini's training, as well as their data centers, like a lot of little tiny optimizations that would have been hard for humans to find out. A lot of people have worked on those processes a long time. They've optimized it as best as they could. Here comes this sort of system and is able to find further tweaks that improve how efficient the system is. This allows the human engineers to focus on higher level tasks. That's what Google DeepMind mentioned in that paper. And some other stuff is sort of optimized and made better by these AI systems. We've covered that in the AlphaEvolve video if you want to see the details. The point being here is that we're sort of beginning to see the first glimpses of self-improving AI. of AI potentially capable of doing AI research, maybe even eventually doing it better than human researchers can. And they continue here, if done safely. And that's the big one, because that's what a lot of people are concerned about, right? This is the thing that kind of freaks people out. This is the red flag, so to speak. Recursively self-improving AI scares a lot of people because if, let's say, we're able to represent its intelligence, right, and we assume that the smarter it gets, the better it's able to improve itself, and the better it is able to improve itself, the smarter it gets, that's kind of the beginning of what they call the intelligence explosion, kind of this exponential increase in machine intelligence. And since a lot of the improvements that it did, humans weren't able to find those improvements on our own, it does seem that a lot of it could potentially be stuff that we don't understand. So that's why they mentioned safety, and we'll talk about safety later. But right now, let's kind of look at what they accomplished here. So they're saying these sort of automations would accelerate AI development and allow us to reap its benefits much sooner. Right, so the Darwin Godel machine is a new self-improving system that iteratively modifies its own code, thereby also improving its ability to modify its own code base. I know you already know this, but it bears repeating. We live in probably the wildest time in human history, bar none. So I'm going to start saying DGM, the Darwin Godel machine, DGM, and aims to optimize the design of coding agents powered by frozen foundation models, meaning that those models, like the models that we use, they're not self-improving. It's not improving or changing the weights of the models. It's sort of working on its sort of a scaffolding, right? So a lot of the stuff is large language model plus scaffolding, which is like tools and code and various functionality that allows it to do stuff. So for example, if Alpha Evolve, here is kind of where the AI, the large language model, goes, right? So we can put in Gemini 2, 2.5, whatever we want goes in here. The rest of it is kind of like the scaffolding. We have the evaluation code that checks to see how good the outputs are. We have kind of the initial database, kind of like where we're starting from. We have the various prompt templates and configurations, so kind of like how we're prompting the model to respond, etc. And this loop runs and eventually, hopefully, comes up with the best program, some optimization that improves whatever it is that we're working on. Notice here, there's a human in the loop, the scientists and engineers working on a lot of these things. It's guiding the model along. So this isn't a fully autonomous AI agent. This is driven by a scientist, and actually on Machine Learning Street Talk, a podcast here on YouTube, they talk to some of the researchers, and you do kind of get a sense that, I mean, not to say they're doing a lot of the work, but their ability to prompt and provide the right evaluation code, etc., plays a big role in how well this performs. So this isn't like an easy button solution. It's still a lot of work by a lot of very smart people. But by relying on these AIs, we're able to just sort of augment what we're able to do ourselves. But the point is that the frozen foundation models, so it's kind of like the models that we use, and they have the ability to read, write, and execute code via tool use, right? So we call this scaffolding. Most people refer to it as scaffolding. So if you saw, all those Pokemon playing AIs, it's just a large language model with some tools and code that helps it, see the screen and take certain actions, etc. It also might have some ability to take notes in some document that it later can reference. So things like that are sort of added to it, that are given to it, that increases its ability to do that thing. Now, what's the big difference between Alpha Evolve and the DGM? A lot of it deals with how do we think of which proposals are good and which are bad? How do we rank them? How do we evaluate them? With Alpha Evolve, they have the evaluation code. So basically for each proposal, there's some code that evaluates how good it is. So you can have an LLM grading it, or it could be some sort of a mathematical thing, right? If you're trying to optimize a car for miles per gallon, for example, anything that improves how far it can go on 1 gallon of gas is good, right? That's as simple as that, right? If you propose something that makes it go further, that's good. And if it, stays the same or decreases, well, that's bad. So proposals that seem to be able to improve the miles per gallon, that gets sort of looked into further, so to speak. And the ones that don't seem to work that way get, put on the back burner or canceled. With Alpha Evolve, it's actually kind of complicated because, an approach might start out looking bad, but over time improve. So it's kind of hard to figure out, like, if you pursue certain paths or don't. Again, Machine Learning Street Talk interviews the developers, and it's pretty interesting. They dive into that as one of the questions. What does the DGM do? Well, it strictly relies on existing benchmarks. One is the SWE bench. SWE bench verified is a collection of tasks from GitHub, I believe. It's verified by humans. It's, filtered by human annotators to ensure that each one is solvable. So it's basically software engineering problems that you would expect to kind of meet in the wild, right? So it's filtered by humans to make sure that they're real tasks. And being able to solve them would kind of imply that this model is able to do things that are similar to what human software engineers would do at their job. And the other benchmark is Polyglot. It includes tasks in multiple programming languages, and it's one of the most widely used coding benchmarks. And they note here, while SWE benches, it's more likely to be in the training data for a lot of these models, Polyglot is more niche and less likely to be included in the frontier models post-training data. So that means basically we want these models solving those problems, not remembering that they've like, oh, I remember, I read about this. I know how to solve it because I remember reading about it. We want it to rely on its reasoning and its abilities as opposed to memory, if you will. Some AI companies will kind of post-train their models on specifically on these benchmarks to improve their results on those benchmarks to make it seem like they're better than they are. So here they're trying to kind of do the opposite. They want to force the model to actually solve these things, as opposed to already having encountered them and just knowing how to do it. All right, but what actually happened? Did it do well or didn't it? Let's find out. So after 80 iterations, so keep in mind, this is kind of our little family tree, if you will, reminding all of us that we're descendants of people that excelled at surviving, right? So here's that kind of like the winning ancestry, if you will, the winning lineage. That's the word. So that's like the winning lineage, the champion breed that becomes the best agent at doing these sorts of tasks. But as you can see here, there's a total of 80. So it goes kind of left to right, top to bottom from, 1, 2, 3 to, it's a little bit harder to tell here, kind of some of these die off, but you got 79 and down to 80. So in total, these are 80 iterations that out of all of them, achieve this one, the one that we're looking for. So we've accomplished that, but we've run a total of 80 generations. It's only 6 progressions on this line, right? From the beginning to the champion, the best agent. But we had to do that evolutionary kind of a search of a total of 80 iterations. So after 80 iterations of the DGM, the coding agent's performance increases from 20% to 50% on a SWE bench. So it improved its accuracy on that benchmark from 20% to 50%. It seems like a big jump. We'll see if we're able to compare that if there's an apples to apples comparison with other models. But it also improved from 14% to 38% on the polyglot. And on the full polyglot benchmarks, it improves from 14 to 30%. And so this is the big point, that this shows that this approach, the Darwin Godel machine, can automatically self-improve to create a better coding agent. And the best version of itself, the best DGM discovered agent, is comparable to that of the checked open source human design state-of-the-art on SWE bench, right? So the state-of-the-art is like the other one that's the best available at the time, or the previous best, right? So they looked at one that have been checked, verified, that are open source, that are human designed. So meaning that humans have tried to design a better coding agent, and they got as good as, the state-of-the-art, the best that we had available was that. This thing beats it. Right, so it's better than humans at improving these coding agents. There's an open source AI agent called Aider, and they're comparing some of the results from their paper to how well Aider does. So they're saying here on Polyglot, although DGM starts with an initial agent whose performance is lower than that of Aider, right? So their brand new kind of a version 0 agent is not as good as this open source Aider. By the way, I forgot to mention this. This is powered by Claude 3.5 Sonnet and O3 Mini. So depending on which benchmark, but those are the AI models that kind of power this thing. So while it begins, its performance is lower than that of Aider. It discovers an agent that far surpasses Aider. So here's that figure, the blue line, that's our DGM. So this is what we're talking about. This is kind of like the full architecture. And the orange and the green, the orange, for example, is without open-ended exploration, and the green is without self-improve. So this is basically they're taking out certain functionalities to see how well it continues to work. Sometimes they refer to this as ablation. So basically, if we take certain pieces out of the equation, does it still function? How much are we relying on the various pieces? So as you can see here, sort of DGM requires open-ended exploration and self-improvement in order to be at its best, to really showcase those results. It requires those things as part of it. But this purple line right here, that's Aider. So as you can see here, on iteration 0, our DGM is not as good as Aider. And as you can see here, it continues creating various iterations until it reaches maybe 13 or so, at which point it jumps up to nearly the level of Aider. And by the very next iteration, it far, far supersedes it. It lands up here. One more iteration and it's near the top of its range. It continues generating various iterations. and then one more, generates one more that gives it a big boost, and then continues to generate more, one more with a big boost, and then it flatlines here. So those iterations, as it's not improving, that's probably generating like this, it kind of is going across and testing all these various things, right? As it kind of goes across the board and it gets to this one and that one improves. So it continues to the next one. So that's why you see those, not flatlining, but parts with no progress. And then once it, continues down this chain, that's where we find the progress, the improvements. So it starts out worse, but by 15 or thereabouts, like it really supersedes Aider by a lot. And these DGM discovered agents are comparable to or outperform handcrafted agents on both benchmarks. So Aider and these handcrafted agents, they were painstakingly shaped by human efforts. So it took smart people a long time, a lot of effort to slowly create those results. Now here's our DGM that blows past some of them, or at least comes close, very close to performing as well as some other ones. And so what they're saying is this new model, this new approach hints at a future in which such ingenuity is automated, evolving through self-referential cycles of continuous self-improvement. So what kind of things does it improve? Well, it automatically improves both the tools and the workflows of how these frontier models are utilized. It can enhance the edit tool to allow more granular file viewing and more precise file editing. Workflow improvements include making multiple attempts to solve a task and using another frontier model to evaluate the best option. Also, interestingly, all the stuff that it builds and improves on, it transfers between models and tasks. So this superior performance, these gains that it's able to accomplish, it can transfer across different models, right? So we have O3 Mini, Claude 3.5 Sonnet, Claude 3.7 Sonnet. As you can see, in each one of these, there's in some of them a huge improvement, right? So we're able to take these improvements that are made to the code, to the scaffolding, transfer it to a different model, and still have massive gains. So this isn't just limited for its own use. There's a transferability here. And it also transfers across different domains, such as from Python tasks to other languages like Rust, C++, Go, and others. Now, in the safety discussion, they do notice that perhaps there could be vulnerabilities that are introduced, things that are not noticed, or some misaligned behaviors that happens. And also, as it keeps iterating, it could become increasingly complex and uninterpretable, right? So human understanding might be lost as it keeps going and building on top of itself. And they do note that at the current time, there's not really a grading system for that, right? So the grades are based on how well it completes the task, not necessarily on how safe the code is or if there's any other issues with the code. As long as it sort of completes the task, we count it as an improvement. But they're saying that another way to apply this technology would be like a self-improvement paradigm. They're saying it could be in principle directed towards enhancing safety, right? So we can apply this same thing, hopefully, to how it self-improve its own safety. The cost of completing a single run of this thing on the Sui bench is about $22,000 US. That's quite a bit. Now, you might be curious, so what are some of the actual things that it does to improve its own code? Well, here's a fascinating case study solving hallucinations. So Claude sometimes tends to make mistakes because it hallucinates using some sort of code, some sort of a tool. And so it says, I ran this tool, but it actually didn't. So it kind of hallucinated doing it. And this, of course, causes issues and errors. So instead of actually making a tool call, it outputs the tool input and output as plain text. Right, so instead of putting the keys into the ignition and then starting the car, it just goes vroom, vroom, and then it just moves on. So they run a DGM for 150 iterations and found 2 promising candidates. And based on some promising lineages, it kind of continues developing along those lines. One fascinating thing it's kind of buried in here. So as you know, sometimes these models tend to kind of fudge or cheat, objective hacking, reward hacking, as it's called. So the researchers put a little code in there to kind of verify that it is indeed improving the code like it's saying. So in this case, they added a hallucination checking function, right? They describe it here, kind of how they implemented it, but it's basically some special tokens that will need to show up at the end. Otherwise, it would sort of show that those tools are not running. And they're saying here that they hide that function from the agent during self-modification, right? So they kind of like hide that piece of code when it's changing its own code. Why? Because they found that objective hacking occurs more frequently when these functions are not hidden. So what that means is this thing is more likely to cheat on these tests when it doesn't think it's being watched. Like if there's a little code in there that's going to check its work, it's like, oh, I better do it right. And if that code's not there, it might go, I think I can fudge these numbers, and just does it. And we've seen these results on some other things as well with Claude and OpenAI models, etc. And they highlight an interesting thing here. They're saying that this kind of argues for the fact that optimizing quantitative measures often leads to undesirable or pathological outcomes. And aligns with Goodhart's law. When a measure becomes a target, it ceases to be a good measure, which humans do as well, right? So if we create some target, some KPI for employees, for example, something that we want to improve, some people will always find a way to kind of game that. Interestingly, it seems that these models do the same. So this is from Sakana AI. They've been doing incredible work. AI scientists. They also submitted one of the first completely LLM-generated scientific papers that was peer-reviewed and passed the peer review. So this is definitely somebody to keep an eye on because they're doing great work, and this is certainly very, very impressive. So again, this is the Darwin Godel machine, which is kind of a cool name, I gotta say. But let me know what you think. Are we at the beginning of recursive self-improvement for these AI models? Does this paper and the Alpha Evolve, do these show that we're kind of entering that self-improvement era? And what do you think that means? Is it scary? Is it exciting? Let me know in the comments. If you made it this far, thank you so much for watching. My name is Wes Roth, and I'll see you in the next one.